All right, so hello everyone. I'm Henry. This is Nolan. We're from Northeastern University, and today we're going to be presenting COBRA, the crater observing bio-inspired rolling articulator. So for a little motivation and background, on the lunar South Pole, there's some areas that are of interest to NASA that contain water ice. Now, they know these areas contain water ice, but they don't exactly know where it is or how much of it there is. So to ideally get more information, they want to send a ground vehicle down to figure out how much and the concentration and such. But there's a bunch of problems in this area. So in this area, there's not a lot of sunlight. They call them PSRs, which is permanently shadowed from the sunlight. So one that is very bad for power generation, and there's also very low temperatures. Another challenge for ground vehicles is the porous regolith. It's kind of like sand, but even more porous. And there are also very steep slopes. And these are all difficult for conventional wheel-based rovers to traverse. So we present our solution, which is, like I said earlier, COBRA. Now, COBRA is a snake robot that has two main modes of locomotion. The first would be sidewinding mode, where it mimics a snake traversing through a desert. And this is it distributes the weight of on the surface area on the sand, so it sinks less, and it kind of slides in a horizontal motion. And the second would be tumbling mode, where the head and tail, they latch together, and with the jolt of the center of mass on the top of a slope, like a crater, it can tumble down like a tire. And this is very good for power because it uses little to no power at all, just to tumble down. It's harnessing gravity.
So to talk a little bit more about COBRA's design, we have 11 identical joint modules, each of which are 1 degree of freedom, and each module contains an actuator, a battery, and voltage regulator. We also have thrust bearings on either side of the actuator to increase our stress capacity, and a unique head and tail module. So to talk a little bit more about those unique modules, in the tail module, because we are aiming to go for the lunar South Pole and look at all these ice concentrations, we're going to house a scientific payload in that module. And we also have a unique head module, which contains all of the onboard computing, its own actuator, voltage regulator, and any other sort of necessary cameras or performance stuff. So to talk a little bit more about how the latching mechanism works, as you can see in the diagram there, we have an actuator that is connected to a central gear with 4 latching fins, and these fins connect to the female cavity on the tail module, allowing it to mechanically lock in place, which prevents any disruption as it rolls down the crater.
So to talk a little bit about the electrical side, it's pretty simple. So each module is powered with its own battery, a lithium polymer battery. And this increases the fault tolerance because, even if one of them fails, the rest of them still have power. The communication wires are the yellow and green there. They're all wired in daisy chain fashion, so they all wire up to the head. And inside the head, there's a Raspberry Pi Zero and the latching actuator for the fins. And these are both powered with a similar lithium polymer battery. To connect to the control laptop, it communicates via Bluetooth to the Raspberry Pi.
So after we built the system, we wanted to do a little bit of testing to verify that all of our locomotion concepts are actually feasible. So this is the mission concept that we designed with all of the different things that we would need to do to get from the lander on the surface of the moon to the bottom of the crater where this ice concentration is. So as you can see, number 2, we're going to sidewind from that lander to the edge of the crater. We're going to connect head to tail to be able to start rolling down the side of the crater. And then at any point on the length of the crater wall, we want to stop. We want to do some scientific measurement. We can do that with our tail module and the payload. That's number 4. And then number 6 and 7, you can reconnect, go down to the bottom of the crater and sidewind until you run out of power, taking scientific measurements the entire time. And then moving away from some of the lab testing that we were doing, this is some more larger testing, which proves some of the tumbling concerns that we had and stability. But as you can see, even on up to 30-degree slopes, we're still very stable and use very little power and are very efficient. Thanks for your time, and we look forward to your questions during the poster session.